Okay, one of the ideas in the course that we've mentioned many times, and it's going to be very important as we move forward, is that when we zoom in on a point on a curve that's smooth, which we call differentiable, that curve begins to look like a line. And there's a lot of things we know about lines that we're going to transfer to what we know about curves. So if we talk about lines, we know that we usually call the slope of the line this letter M. Okay, so I'm going to refer to M. Now, we know that if M is more than 0 for a line, then your line increases, which to us means the y values get larger as the x values get larger. Okay, as you move to the right, the y values get bigger. And we know that if M is less than 0, the line decreases, which means as the x values get bigger, the y values get smaller. We know that if the slope is 0, you have a horizontal line, or we could say your line is constant. So I'll put constant or horizontal. And there's one other possibility, is that your slope could be undefined. And for lines, that means you have a vertical line. So we know that smooth curves, curves that are differentiable, look like lines when you zoom in. So we're going to start to transfer some of this information to curves. So let's make some guesses that what would make sense in this situation, transferring this information to curves. Okay, so if the slope of a curve is positive, now the thing that finds slopes of curves is this machine we call derivative. Okay, so f primed is what finds the slope. So this is a function. If you give it an x value, it spits out slopes of your function f. So if f primed of x is positive, now positive on an interval, so it's got to be an open interval because we can't have closed interval because no slope happens at endpoints, okay? But if our slopes are positive on this interval, then that means when we zoom in on the curve, we'll look like lines with positive slopes, which means I should be increasing, okay? So let's write then f of x should be increasing on that interval. And I'm going to include the endpoints there, and you'll see why in a second when we prove this. Okay, but I don't think this is a big leap. Okay, you take your slope finder. If your slope finder is positive on an interval, then your function is going to increase on the interval because our curves are going to look like lines when you zoom in. And let's reverse that. If f prime of x is less than 0 on an interval, then your function should decrease. And again, I'm going to include the endpoints of your interval there, and you'll see why on the next slide. Okay, on this slide, I'm going to prove the increasing statement from the last screen. If you're not really interested in the proof, you can skip ahead. It's not vital that you know the proof, but I think it's nice to see where the things that we're saying can connect to what we're trying to prove in the end here. Okay, so we're saying if the first derivative is positive on an interval, a to b, then f will increase on the closed interval ab. Okay, let me write down here what it means to be increasing. Okay, this is a pre-cal definition. Okay, f increases on an interval, and since we're talking about a to b, I might as well continue to use a to b. Okay, if x2 being bigger than x1 implies that f of x2 is bigger than f of x1. That's what it means to increase. Okay, it's saying if the x values get larger, which means as we move to the right, then the y values at those x values also get larger. Okay, so that's what we're trying to show in the end here, is that f is increasing. So we're going to get there, but we're going to start with this fact right here. So we know that the first derivative is positive on a open interval AB. So I've drawn AB as a closed interval, but we know that every dot between A and B, the slope of the curve is positive there. All right, now here's what we're going to do. We're going to choose at random. We're going to go into a paper bag, and we're going to choose two x values somewhere between A and B, and they could include A and B. Okay, so I'll explain that as well. Okay, so we're going to choose x2 and an x1 on the interval AB. And we'll include the endpoints here. All right, and the only stipulation here is that I want x2 to be bigger, so that I can know which one's larger in my calculations here. Okay, now here's what we're going to do. We're going to calculate this number right here, f of x2 minus f of x1 over x2 minus x1. Okay, this is the average rated change of f on the interval x1 to x2. The mean value theorem says that that has to be equal to f primed of c for some c on the interval x1, x2, the open interval x1, x2. Okay, so that's what the mean value theorem guarantees us. I told you the mean value theorem was going to be important in the days to come, and here's one of the reasons why. Okay, so there's a c that lives somewhere between these guys where this is true. What do we know about f primed on this interval? Okay, f primed is always positive, right? That was the stipulation. So I'm going to erase this and replace that with greater than 0. Okay, now x2 minus x1. Okay, what do we know about that? Well, if x2 is greater than x1, then x2 minus x1 has to be positive. So that means I can multiply both sides by this number, and I don't have to flip the sign. And this is never going to be 0 because x2 is bigger than x1. So if I multiply both sides by x2 minus x1, that gives me that f of x2 minus f of x1 is greater than 0, which means, okay, f of x2 is bigger than f of x1. And since we chose x1 and x2 at random, we could have done that for any points in this interval. This will be true for all points on the interval. And therefore, we can say that f increases on a to b. Now, why do I include the endpoints here? Because I could have chosen a and b to begin with, and the mean value theorem still guarantees me what? That f of b minus f of a over b minus a is equal to f prime of c for some c between a and b. So the endpoints are included in the increasing definition. We've been using f prime of x just to find slopes in the last unit, but now we're going to be interested in analyzing f prime as a function. In this case, we're going to analyze its sign, which means we're going to be involved with sign charts now. Okay, so here's an example. Find the intervals of increase and decrease for this function 1/5 x to the 5th minus 3x cubed plus 6. So we need to analyze the sign of the first derivative to do that. So f prime of x is equal to 5 times 1/5 will give me 1, so x to the 4th minus 9x squared. I'm going to set this equal to 0 because the numbers that go on my sign chart are whatever makes this derivative 0 or undefined. Nothing makes this derivative undefined because it's a polynomial. So I need to find the zeros. So the zeros are going to be whatever numbers solve this equation. So after I factor, and I'm going to factor one more step, I'll be just about there. Okay, so I can clearly see now that there are three numbers that will make the first derivative 0. They are 0, 3, and negative 3. And those numbers are going to go on a sign chart to analyze. So here's a number line, and we partition the number line at these values. So -3 and 0 and 3. I'm going to label my sign chart. This is sign chart for f prime, not for f. Now let's test a number in each interval to determine what signs each interval takes on. For example, when x is bigger than 3, let's say 10, I'm going to get a positive times a positive times a positive. I don't need to know the exact numerical value, I just need to know the sign. When x is a number between 0 and 3, like 1, I'm going to get a positive times a negative times a positive. Overall, a negative. Between -3 and 0, like a -1, I'm going to get a positive times a negative times a positive. Still negative in this interval. And if I use a number smaller than -3, like -10, I'll get a positive times a negative times a negative. Overall, a positive. Okay, so this sign chart now will tell me what f does on these intervals. This is pretty neat. Okay, so let's see here. F will increase on intervals where the first derivative is positive. So that's going to be -infinity to -3. Obviously, we'll use a parenthesis at -infinity because we never get there, but I'll use a bracket at -3. Okay, and on the interval 3 to infinity. Similarly, f decreases on intervals where the derivative is negative, which are -3 to 0 and 0 to 3. Okay, if you're asking if you can combine those two intervals into one, the answer is yes, as long as your function is continuous. And in this case it is, so you could combine those two. Okay, so you could start to sketch a decent picture of what this graph does based on where it increases and decreases. You can also determine what happens at -3, 0, and 3. If my function increases before -3 and then decreases after -3, then I should see a local maximum there. If my function decreases before 0 and then continues to decrease after 0, I'm not going to see any maximum or minimum. I'm going to see a saddle point. And if my function decreases before 3 and then increases after 3, I should see a local minimum. So that will lead us real quick to what's called the first derivative test for local extrema. Okay, if your function is continuous, that's a stipulation of these facts here, and if f prime changes from positive to negative, that means your function f changes from increasing to decreasing, then you'll have a local maximum at C. Okay, this one talks about local minimum, and then this one talks about no sign change happens at C, then you'll see neither a max or min, you'll see a saddle point. Now, one of the great things we can do with this information is we can look at the graph of the first derivative and make conclusions about the graph of f, even if we don't ever see the graph of f. So again, we analyze the sign of this function to talk to us about the graph of f. So we're going to look at the y values of the first derivative. Before -3, so from -infinity to -3, f prime is negative. So what does that mean? Okay, that means your function should decrease on that interval. Then your first derivative is positive, has positive y values from -3 to 2. So f primed is positive on this interval, -3 to 2 open, which means f is going to increase on the interval -3 to 2. We go negative for your y values of f primed from 2 to 6. So f primed is less than 0 on 2 to 6. So what's f going to do? F's going to decrease on 2, 6. And finally, your first derivative is greater than 0 again from 6 to infinity. And so that means f is going to increase on closed interval 6 to open infinity. Okay, that also tells us that right here, the first derivative changes from negative to positive. That's going to be a local min at x equals 3. We don't know the y value, and that's okay. We know locations, though. Local min at negative 3. When the first derivative changes from positive to negative, that's going to be a local max at x equals 2. And again, the first derivative changing from negative to positive is going to be a local min at x equals 6. Now, I have the graph of f stacked on top of the graph of f primed, and we'll get to take a look and see how accurate we were with our conclusions here. Okay, so I'm going to go ahead and start to connect some of these dots here. So we said that at x equals 2, I should see a local max on the graph of f. So if I draw a line that goes straight up, because I've stacked these graphs, I should see a local max, and I sure do. I said I should see a local min at x equals 6. And if I draw a line going straight up, I do. Now, I said I would see a local min at x equals negative 3. Unfortunately, I didn't have enough space for this graph to be seen, but if this continued down, I would expect to see the local min at that spot. And take a look at the intervals we talked about. Bigger than 6, we should say f increased, and it is. Between between 2 and 6, there we go, we said f should decrease, and it does. Between negative 3 and 2, we should see that f increases, and it looks like it does. I don't see that happens less than negative 1 point something. And if we could see the whole graph, I would expect to see f decreasing from negative infinity to negative 3. So really powerful tool is first derivative as far as analyzing the behavior of your function f without really having to see its graph.